Bueno, damos comienzo a la primera sesión de la mañana de Galaxy Formation and Evolution y el primer disertante es Vladimir Avila-Reese, que nos va a hablar de Evolution of the Intermediate Massive Galaxy Population, Obscure and Unobscured Star Formation, Submillimeter Galaxies and Quenching.
Thank you, Mario. Good morning, everybody. It's a pleasure to be here. So very fast, this talk will be a continuation of Aldo's talk about the connection all the time of empirical observations with theory. But the first thing will be completely empirical. So we have two questions. One is the galaxy stellar mass in the era of large galaxy surveys at different redshifts, we are able now to determine the evolution of the galaxy stellar mass function and the star formation rate versus stellar mass relations since redshift 0 to high redshifts. You can see here we have the galaxy stellar mass function since redshift 10 to the present day, and here is the star formation rate versus stellar mass relation from redshift 0 to redshift 5, 6. So the question is, are both consistent with each other? If we can connect, because the star formation rate is the way, the channel to grow galaxies in stellar mass, to evolve in the galaxy stellar mass function. We have the continuity equations that connect the evolution of the galaxy stellar mass function with the star formation rate, as you can see below. So when the people start, for example, at redshift here 2.2 with the galaxy stellar mass function, use the star formation rate stellar mass relation at this redshift, which is typically a power law, and you evolve this galaxy stellar mass function with these star formation rates. At redshift 1, you will have here, which is the blue line, the galaxy stellar mass function evolves a lot. If you go to redshift 0.5, even more, using all the time the star formation rate stellar mass relations determined in surveys galaxy by galaxy. This is a problem. So the way to solve this problem, some people claim it, is just using proposing that the star formation rate stellar mass bends, for example, here at masses 10.5 in log, should be much lower than the power law. And in this way, the galaxy stellar mass function with these continuity equations evolves as the green line here, more or less, more reasonably, yeah? But even in this case, the evolution is too much. So people is suggesting that, for example, the IMF, the initial mass function, should change, or that the mergers play a big role in the evolution of galaxies. This is a conflict, but there are however, there are some caveats in this approach. First, we use only the mean star formation rate stellar mass relations, not taking into account the scatter. This is very important. The other thing is that the star formation rates and the stellar mass are assigned in this kind of studies to determine the star formation rate versus stellar mass relation, galaxy by galaxy, from redshift samples using different traces for the star formation rate, the UV, far infrared, H alpha, and others. And each one of these tracers has its own selection function, which with complicated mixes of incompleteness in each one of these tracers at the same time. So, and the role of the mergers is also very uncertain. So all these things make it very difficult to make some inference about the evolution of the star formation rate and the galaxy stellar mass function. The question, is there an alternative way to determine the star formation rate versus stellar mass at different redshift relation, including its scatter? And also, what is the contribution of the dust obscured star formation? So it's not going, okay. Okay. Regarding the dust obscured star formation, you know, the dust obscured star formation typically is calculated as the ratio of the star formation traced by the far infrared over the total star formation rate traced by infrared plus UV. So the determinations typically give a strong dependence with mass, but again, these determinations are based on galaxy by galaxy studies in samples which are very different. And the question is if we have another way to do all this exercise. So it's not working this. No. Okay. I think the battery is low. So we propose a unified demographic approach, published in a paper recently. Not so recently, okay. The idea is to use homogeneous information from dresset surveys of the far ultraviolet and infrared luminosity functions and connect these to the galaxy stellar mass function of star-forming galaxies at different redshifts. This way we can constrain the evolution of the conditional distributions of the far ultraviolet and infrared-based star formation rates given MS, those that are shown below. These are the mean of these conditional relations are the relations, the star formation in UV versus stellar mass and the star formation in R versus the stellar mass. No? Okay. The main idea is very simple. The idea is to connect through this convolution the observed luminosity UV function with the observed stellar mass function of star-forming galaxies. This is a convolution, and here is the conditional probability of a given star formation, of the star formation rate given the stellar mass. We just can pass from the UV luminosity to the star formation rate in UV by assuming a constant, the Kennicott transformations. And this is a completely empirical abundance matching approach. In this approach, the idea is that we have the observables. It's not working, this. ¿Allá? Okay. Tarda mucho en cambiar. The idea is to use as observables the evolution of the luminosity function in UV, the evolution of the star formation of the galaxy stellar mass function of star-forming galaxies. From this, we made a very extensive literature compilation and homogenization, taking into account biases and quantify adequately the random uncertainties. And the same we did with the luminosity function in the infrared. The same approach for the, and this way we can now. No, it's not working. This. Okay, I have to use this. I think. So the idea now is just to having these observables. Now constrain this conditional probability distribution for the UV star formation rate or the infrared star formation rate. We have to parameterize these functions, for example, the star formation versus stellar mass in UV or in infrared. We parameterize, and solving this equation, we can constrain the parameters to determine how evolves the star formation traced by UV and the star formation traced by infrared luminosity as a function of stellar masses. We have complicated parameterizations and blah, 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 but the main thing is that with the observations we can constrain, and here are some results. How evolves the star formation rate at different masses. You can see here the star formation rate as a function of redshift for different mass beams, from the low mass to high masses. The shaded areas is the scatter of our determinations, and the dots are several measurements galaxy by galaxy. We can see a very good agreement with the galaxy by galaxy measurements and our demographic inferences. But in our case, we are able to extend to all the regimes and to modulate the scatter, which is very important. So our main conclusion is that since our approach is by construction consistent with the galaxy stellar mass function, and we find this good agreement with the observations of galaxy by galaxy, so there is no any inconsistency between the evolution of the star formation rate versus stellar mass relation and the galaxy stellar mass function. There is no need of extreme IMF and other things. Here I am plotting the specific star formation rate versus stellar mass. Here is called the mean sequence with the scatter, and comparing with several observations at redshift local galaxies. Very good agreement. We can even separate between the contribution of dust obscurity, which is the red one, and non-obscured star formation, which is the blue one. The same plots we can do for different redshift beams, up to redshift 2.5. And here we are comparing with the candle survey in the paper by Whitaker et al., which are the circles, and we see that there is very good agreement even in the composition of star form of dust obscured and non-obscured. This plot resumes the evolution of the dust obscured fraction as a function of stellar mass. So we have here for the local galaxies, this is the ratio of infrared star formation rate to the total star formation rate. So when this is 1, it means that the galaxy is totally obscured by dust. Yeah. So the main thing is that this fraction strongly depends on mass at all redshifts. There is a weekly evolution with redshift. The major evolution is between redshift 0.7 to today. You can see the massive galaxies become more transparent with time. They start forming, all these are star forming galaxies. And for redshifts larger than 1, all galaxies more massive than 10 to the 10 are very highly dust obscured, as you can see here, or more than 80% of dust obscured star formation. So all this was completely empirical, but in the approach that Aldo commented early in the morning, the semi-empirical approach, the Empire, we can connect all these observations that I showed you, the galaxy stellar mass function, luminosity functions, etc., to the dark matter halos in n-body simulations. And we can have individual evolutionary tracks. For example, here I am showing the stellar mass growth histories. These are average tracks of how galaxies grow, massive galaxies today, dwarf galaxies today, and the color is plotting the dust obscured star fraction. You can see that galaxies typically go from transparent to dust obscured. But interesting, the most massive star forming galaxies, even the obscuration become more transparent at lower redshifts. We can also plot the far infrared luminosities, which are associated to the submillimetric galaxies. We can see that the highest luminosities in infrared are at redshifts between 2 and 5. All these regions are ULIRGs or hyper-luminous infrared galaxies. And these galaxies typically then quench and evolve to the present-day ellipticals, which a bit, we can here plot the same as a function of the halo mass. So these galaxies that were very highly start forming in the dust obscured regime as higher LIRGs or ULIRGs, today end in clusters or groups. These are the predictions. So we can also generate the light cones with the Empire. For example, this is a light cone of 100 square degrees in the sky, where we are showing here the flux sources, all flux sources above 0.26 microjanskins at 1.1 millimeters. This is a work in process with Nava Moreno, who is a PhD in AOE. What we see here is that the brightest sources in the sky are the ones that are green or black or white, are found at redshifts in between 1 and 4. And they typically are in very clustered regions. There are no these sources in voids, for example. Yeah? These are predictions that we can do for example, for the Toltec survey. Toltec is a camera that will be installed, is already installed in the 50 millimeter telescope, the largest one-dish telescope in the world, which is in Puebla, in Mexico. And this Toltec will do surveys of the sky in different, with different depths, different in 1.1, 1.4, and 2 millimeters. So with Empire, we can do predictions of how will be, as you seen in the light conus. For example, we can predict the integrated number counts that we will observe in this survey at 1.1 millimeters in 0.3 square degrees region of the sky. This is the black line. And here we compare it with many previous determinations, which are very limited. Yeah, you have seen there are some surveys very small, others are very deep. This Toltec will give a very homogeneous survey, and in our lambda CDM based model, we can predict how observations will be and compare in a very fair way observations and predictions with the semi-empirical approach. So my concluding remarks very fast, the completely empirical approach using the joint evolution of the completing volume galaxy stellar mass functions and luminosity functions allows us to attain a self-consistent picture of the obscured and unobscured star formation history of galaxies. And we have found that there is no any inconsistency in current observations between the evolution of the galaxy stellar mass function and the measurement of the star formation rate at different redshifts. We have found that the dust obscured star formation strongly depends on mass and weakly with redshift. And when we introduce all these observations to the semi-empirical approach, connecting with dark matter halos in the simulations, we have found that star-forming galaxies evolve from unobscured to dust obscured. Only the most massive become more transparent at lower redshifts. Sorry. And that, just to finish, we have found that the U-Lyr and hyper-Lyr galaxies, sources, inhabit halos of 0.5 or 5 to 10 to the 5, 10 to the 12 solar masses at redshifts between 2 and 5. And our mock icons will be very useful to compare fairly observations in the submillimetric galaxies with theoretical predictions. Thank you very much.
Okay. Let's thank Vladimir. Questions? There.
Hi, very interesting talk. Thank you very much. Maybe I missed this, but I wanted to ask if you have any idea of the black hole fraction in these sublimated galaxies or ULIRs that you see at higher redshift, or if that's active or it's inactive. Thank you.
Sure. Yeah, we have in the semi-empirical approach also the black hole, the supermassive black holes, as Aldo showed it in the morning. And I don't remember, but I think at these high redshifts, the supermassive black hole to stellar mass ratio is very high. Yeah. So these are galaxies that probably will quench because of the AGN feedback given by the accretion onto the supermassive black holes that grow very fast at these epochs.
Okay, no more questions. Let's move. Let's thanks again to Vladimir.
Thank you.
So our next speaker is Gabriel Azevedo and Galaxies in Transformation, constraining the structural and stellar population parameters of galaxies undergoing RAM pressure stripping. Well,
hello everyone, I'm Gabriel Azevedo. I'm a PhD student at URGS in Porto Alegre. And thanks to Professor Yara's presentation, my work here will be a lot easier because I'll also talk about jellyfish galaxies, but with narrowband surveys. So actually I will talk about two different works, one that is being led by a collaborator of mine, Yashigo Daleke, and another one that I am currently leading. So I'm kind of representing the whole research group here, not just myself. So starting with a brief introduction, we know that for dense environments, like for clusters and groups, the fraction of spirals and irregular galaxies is lesser than the ones of ellipticals and S-zeros. And that is because in these dense regions, the spiral galaxies suffer a lot of processes that may quench up the star formation and change their morphologies. And one of these processes is the RAM pressure stripping. As we saw earlier, when galaxies moving in high velocities in clusters or groups, they suffer the RAM pressure stripping because of the intercluster gas, and the gas of the galaxy can be stripped from their disk. And in this context, the jellyfish galaxies arise. They are the most extreme cases of galaxies undergoing RAM pressure stripping, and the gas stripped from their disk form these tails these structures that resemble tails. And this morphology is mainly seen in the H alpha, as we can see here in red in these images, because of the gas ionized by star formation. Another important feature of the jellyfish galaxies is that they have, in average, higher star formation rates compared to other star-forming galaxies in the same environment. So the rim pressure is a process that at first enhances the star formation of the galaxy, but may end up quenching them. I have been working with them for a while now, and a few months ago we just published a paper where we analyzed, we performed stellar population synthesis in the whole GASP sample. There is a survey that observed dozens of jellyfish using the Muse spectrograph. If you are interested, please check out their paper, but this is not the focus of this presentation. I will talk now about the work that is being led by my collaborator, Yashi Gondalekar. He's a student in India, and he's from computer science. So he's applying some AI methodology to classify jellyfish galaxies. So this work is focused on finding stripping candidates in the clusters of Fornax, Antilia, and Hydra. With this methodology, we found 21 jellyfish galaxies in these three clusters using the photometric survey of the S+. That is S+ is a photometric survey that is mapping the southern hemisphere. But the interesting thing about this work is how these classifications are done. Usually the most common way to classify jellyfish galaxies is to use optical images to assign what we call J classes. That goes that goes from 1 to 5, depending on the intensity of the visual signatures we can see of the stripping. But this is not much reliable because it depends on our eyes. So what Yash does here is to apply a self-supervised learning method to help the classifiers to build a more robust analysis. So briefly, what the code does is all the classifiers assign visually J classes to all the galaxies in the sample, and the code takes for each one. It sees what galaxies are the galaxies that are closer to it in the morphological parameter space, and then computes the mean of the visual J classes and assign it as a, let's say, SSL J class. This is not to substitute the visual inspection of the jellyfish, but to help us to build a more robust sample. And using this, we then identified more than 50 galaxies in these three clusters and analyzed morphological and stellar parameters of them. And some of the main results is that we found some trends in the morphology of these galaxies. We also find that their star formation rates are higher than the other clusters members, what is already expected. And we developed this semi-automated pipeline to classify the jellyfish galaxies. This paper is almost finished, so stay tuned to archive. At any moment it can be submitted. But that's it about Yasha's work. And now I will focus on the work I am currently doing. That is very related to this. We are also searching for stripping candidates as part of the PFS collaboration. PFS is the prime focus spectrograph. It is a multi-fiber spectrograph that is about to become operational in the Subaru project, the Subaru telescope. And we want to select possible targets for observing with it. Then we need to first classify and detect the jellyfish galaxies. So as a starting point, we take this question here, which is an open problem in the literature. That is, if there is any connection between the rim pressure stripping and the AGN triggering. maybe yes, maybe not. It is still very open. Some papers based on the GASP sample and other observations in the literature point that yes, there is a higher fraction of AGNs in the jellyfish compared to other star-forming galaxies. However, in the paper of Romano Oliveira from our research group, we found more than 70 jellyfish galaxies in a single merging cluster system of Abel 901-2, and only 5 of them are probable AGN hosts. So we don't know if these discrepancies in the results are because of some bias in the masses, if there is something related with the environment where they form, or something else. It's still open. So to help to shed some light on this question, we want to select both stripping candidates and AGN hosts to observe the PFS. And to that, we are using the images and catalogs of the Hyper Supreme camera that observe the same fields that will be observed by the PFS. And it's a photometric survey, and we intend to use a methodology same to what I presented earlier from Yashi's work. So we selected all the H-alpha emitters in a redshift between 0.23 and 0.26, so that the H-alpha line falls exactly inside this narrow band here, so we can see the jellyfish features more easily this way. Meanwhile, while we were doing that, the DESI instrument also released their early day release. So we decided also to use the spectra from DESI to our work. We found more than 5,000 H-alpha emitters using the HSC, but only a bit more than 200 of them had spectra from DESI. So we opted to use only this smaller sample with DESI spectra. It is smaller than the other one, but we have more reliable redshifts here. So we can use it as a starting point. We are currently at the stage of performing the visual classification with the collaborators. We are using the Zooniverse here, but this is not finished yet. And also we modeled the emission lines. We're using DESI spectra to construct these emission line diagrams. We can see here that most of the galaxies in our sample are powered by star formation, but we have some AGN candidates. So a bit about the conclusions and future steps for this work is that first, the narrowband surveys provide a good chance to identify these jellyfish galaxies. The visual inspection, it is still necessary, but the self-supervised learning method helps us to improve that. And we also intend to use the same methodology with the HSC and DESI data. And we hope to observe these jellyfish galaxies we detect with the PFS, and also compare with other data like the LOFAR. And we are also starting to apply the same methodology in the JPass. That is another photometric survey. And that's all. Thank you very much.
Questions, comments?
Thank you. It's possible to have the radial distributions of the jellyfish galaxies in different bands, because you say that the specific star formation rate is higher typically for your jellyfish galaxies than the control sample. So it will be interesting to see how is the regime of star formation is more concentrated in the center. Why the specific star formation is higher in these galaxies that are being deploying of gas? Probably is because there are a lot of concentration to the center. It would be nice to see in several bands how is the radial profile. Is possible, or do you have some estimates of that?
Good question. So actually, I've done something more or less like this in my paper here. I have a question, an image to show you. Here, we constructed these radial profiles of the various parameters of the galaxies, including the specific star formation rates. Both for we separated the sample, we divided the sample by the what we call the strip intensity. That is something similar to the J classes I told about, but not exactly. So we have here the mean star formation rate radial profiles for these different intensity groups. And we also did the same thing, but dividing the sample into different bins of masses. So what we see here is that we not focused on this specific topic you asked about if it's more compact or extended, but we saw that in an overall picture, it is somehow it's close to what we have in the literature for, let's say, sorry, I forgot the name. The gases that have high star formation rates, starbursts. Yeah, that's it. But we did not. I don't know say if it is more compact or extended.
One last quick question here.
Hi, nice work, nice talk. Can you explain better the maps of the H alpha? I think in the last slides.
These ones?
Yes.
So here these are the images we are using in this universe for the classification, and these are the images in different photometric bands of the HSC. We have here the greasy images that are the sum of all the broadband images, and we have in the contour, the red contour here is the emission of the narrow band NB816. That is in principle the band that encompasses the H alpha and N2 lines. So this contour here is supposed to be the H alpha emission. And we also have here the difference between the I band and the narrow band, which would be something like taking out the continuum from the gas emission. And here we have the emission lines modeled with from the DESI spectrum.
Okay, let's thanks again, Gabriel, and move to the next speaker. Katia Slodkowski Clerici, going to talk about stellar population properties of massive compact galaxies at redshift 0, evidence of diversity in the formation pathways.
Good morning, everyone. I'm Katia. I am PhD candidate from Universidade Federal do Rio Grande do Sul in Brazil. Today I talk about the first part of my PhD, the stellar population properties of massive compact galaxies at redshift approximately 0, evidences of diversity in the formation pathway. So in low redshift, it's possible to see a diversity of the galaxies, different morphologies, different forms, different colors, mass, size. And despite the diversity, it's possible to classify these galaxies in few groups, like in this case, using a color magnitude diagram. It's possible to separate these galaxies in star-forming galaxies and quiescent galaxies, where star-forming galaxies are rich in gas and form assignative numbers of stars, and quiescent galaxies have few gas, don't form more stars, and have a stellar population old and metal-rich, for example. And this classification is not only in the low redshift, it's possible to see in high redshift this classification. Here in this picture, you have the size and the mass relation. It's possible to see, you can find star-forming galaxies and quiescent galaxies here in high redshift. Here, for example, redshift approximately 1.75. But when you compare these galaxies at high redshift with galaxies at low redshift, it's possible to see the galaxies with the same mass are totally different between these two redshift. For example, these galaxies at low redshift, at a high redshift, are extremely more compact than galaxies at redshift approximately 0. Okay? And it's difficult to study these galaxies, especially the quiescent galaxies at high redshift, because this galaxy is very small, it's very faint. So it's difficult to study these galaxies as a large sample of the galaxies. And then it's necessary to search for alternatives to investigate these galaxies. And an alternative is to look for analogs of these galaxies in local universe, in redshift approximately 0. So, for example, you can look for a relation, size-mass relation in local universe, and you can search compact massive galaxies has outliers in this relation because have the similar stellar mass and the similar size. So, the goal of this work is to investigate the star formation properties of a large sample of massive compact galaxies in order to constrain the formation and evolution of these galaxies. So here you have 4 pictures of massive compact galaxies from your sample. So here you can see some examples. And to select your sample, you use a new criteria. You create a new criteria for select the sample of the galaxies. For that, you use 2 relations. The size velocity dispersion relation and the velocity dispersion mass relation. And the compact massive galaxies in this case are outliers in these 2 relations in the same time. So the massive compact galaxy here is showing in red. So to be massive compact galaxy, it's necessary to be outliers in these 2 relations. You use the velocity dispersion 2 as a criteria to selection because you're looking for a group of massive compact galaxies with old ages. Okay? To compare the stellar population properties, you select a sample of control galaxies, quiescent galaxies, with regular size, and then follow these 2 relations here. You match these control sample galaxies in redshift with massive compact galaxies. Okay. So to investigate the properties, stellar population properties of this galaxy, the age and the metallicity, you use spectral synthesis. In this case, you use the code PPXF. And additionally, to determine the alpha enhancement of these galaxies, you use some spectral indices and this equation here. So to compare your results, you compare your results at a fixed velocity dispersion. And why that? Because the stellar population properties of quiescent galaxies are better correlated with the dispersion velocity than other properties of the galaxies like stellar mass or dynamic mass. So you compare the stellar population properties at fixed velocity dispersion for these two samples. And for that, you separate these galaxies in 6 bins, velocity dispersion, and you calculate some percentiles for these galaxies. And also you do a statistical test, KS test, to comparing these two samples to see the significance of your results. So here we show the age as a function of velocity dispersion. Here is possible to see the results of percentiles. Sorry about that, I don't put a legend for that. But the crosses here are for control galaxies, and the scatter here, blacks, are for compact massive galaxies. And here you have the alpha enhancement as a function of velocity dispersion. For these two properties here, you find two different results in different ranges of velocity dispersion. At fixed velocity dispersion, for low velocity dispersion, you see the massive compact galaxies are older and more half enhancement than control galaxies. But this change for high velocity dispersion. In high velocity dispersion, they have similar age and similar alpha enhancement than control galaxies. But this change for melariste. So here you have melariste as a function of velocity dispersion. And when you compare the control galaxies with massive compact galaxies, you see the massive compact galaxies have lower metallicity than control galaxies at the fixed velocity dispersion, but in this case, in all the range of velocity dispersion, not only in the low range. So also, you see some overlap between these two, these properties between these two samples. This overlap don't mean, for example, these galaxies come from the same subgroups of quiescent galaxies at high redshift. Because you conclude that the massive control galaxies and control samples descend from different subgroups of the high redshift quiescent galaxies because they have a different significative on the stellar mass. They have a different significative here, where compact massive galaxies are less massive than control galaxies. So it's not possible the control galaxies to be descendant of the compact galaxies in your case. Okay. Additionally, our result cannot be explained by a variation in initial mass function. Because that, you find the control massive galaxies are older, are more alpha enhancement, and have a lower metallicity than the control sample, especially in the low velocity dispersion. These results is only possible explained by a variation in initial mass function when you have, for example, compact massive galaxies having higher and metallicity and higher alpha enhancement, or lower metallicity and lower alpha enhancement. This is not your case. You will not find these results. So it's not possible that the results are completely explained by initial mass function variation. Your suggestion, it's possible to find the suggestion in other papers about early type galaxies, but this first time in compact massive galaxies, is the variation in the dark matter fraction in the galaxies. So for example, you have a first explanation. This is about the truncation of a star formation for these galaxies. So in this case, you suggest the compact massive galaxies form less generation of stars than control galaxies. So in this case, they have less stellar mass and less melaricity. How can I see in your results? Another explanation is if this galaxy is formed in a concentrate halo dark matter in the high redshift, it's possible that these galaxies have a higher velocity dispersion for the stellar mass. Then they have this higher velocity dispersion, they have a low stellar mass because the higher concentrate dark matter, then they have a lower mellaristic. So this can be a possible explanation for your results. Moreover, is important to note that this is not possible the unique explanation for your results because of this plot here. You have the mellaristic as a function of velocity dispersion. It is correlate for stellar mass. In this case, only for massive compact galaxies. We see this at the fixed velocity dispersion. There is a variation between mellaristic and star formation rate. Mellaristic and stellar mass at fixed velocity dispersion. This case shows them, maybe in some cases, they have a regular mellaristic, a regular mass. So it's possible have another explanation for this case. So maybe, for example, so galaxies pass for a compactation, but maybe not. Maybe some compact massive galaxies, in your case, always be compact in your evolution. So here I show two examples from literature. These galaxies here, both are compact galaxies. You see two different, totally different results for diffraction of dark matter. In this case, you have compact galaxies or a higher fraction of dark matter in your system. But in this case, you have a galaxy, a compact galaxy, in this case is a relic galaxies, with a depth of the fraction of dark matter. So we see that your results suggest evidence of diversity information pathway of these galaxies. It's not only one explanation. This is only the beginning of the project. Now it's necessary to investigate other properties of these galaxies. For example, we start looking data of photometry to investigate other properties and to confirm or not the results you find in this first part of the job. So thanks so much.
Okay, we have time for one quick question. Over there, Aldo.
Nice talk. So could you come back to the previous slide? So on the figure that you are showing of the metallicity, I was wondering, so here it's clear that the stellar mass and the velocity dispersion trends are very correlated. And you increase velocity dispersion, you also increase in the stellar mass. So I was wondering if that trends are also driven in your previous results where you were plotting as a function of velocity dispersion and comparing to the control and your compact sample, if those trends are just driven by stellar mass and not by being compact.
Okay.
Could you comment on that?
Okay. For control galaxies, you not see this trend, for example. I don't know if it's that. Well, you have this result, you not see this trend like you see in compact massive galaxies.
Okay.
I don't know.
We can discuss later. Thank you.
Let's thank Katia again and move to the next speaker. Is Leandro Sesto, Reconstructing the Star Formation History in an Intermediate-Age Merger Remnant.
Okay, hello everyone. Thanks for coming for my talk. Can you listen to me? I am Leandro Sesto, not Leonardo, but you can call me Leo, it's okay. I am from Universidad Nacional de La Plata in Argentina. And Today I'm going to talk to you about different stellar systems associated to an intermediate-age merger remnant. And we are working in this project with the people of my group in La Plata, the SEC group. They are my collaborators. And in this group, we are interested in study early type and merger galaxies, and also globular clusters and UCDs. And to do that, we mainly use optical and infrared photometry and spectroscopy. So I'm going to focus my talk about the UCDs, ultra compact dwarf. As you can see in this plot here, this is an example. We have different stellar populations. We have galaxies, globular clusters, and we have the compact ellipticas. And between them, in this range between mass and effective radii, we have the UCDs. There isn't a unique definition of this object, but in a broad sense, we can say they are bright objects, really bright, and they have masses greater than 10 to 6 solar masses, and they have effective radii between 3 and 100 parsecs. We also know that these objects are combined for two different kinds of objects. They are the tail of the most massive globular clusters, or they are the nuclei or the triple nuclei of dwarf galaxies. And a good place to study these objects are mergers of galaxies. Mergers of galaxies in the local universe. So in our group, we have a big sample of different kinds of galaxies that share this information. But today I'm going to show you only the first result we have for UCDs in NGC 1316, also known as Fornax A. This galaxy is the most massive galaxy in the Fornax galaxy cluster, and is one of the most brightest radio sources in the southern hemisphere. This galaxy has a really interesting target because it shows different features that indicate that this galaxy has suffered a merger in the recent time. Among them, we can emphasize ripples, loops, tails, shales, a contra-rotating disk of stars in the inner zone, and also a complex structure of dust in the central region of the galaxy. To analyze these objects, we get data from GMOS camera. The GMOS camera is mounted in the Gemini South telescope in La Serena. And in the past, we studied the globular cluster system associated to this galaxy. First, we do that using photometry. We get 8 deep fields in different bands, and we analyze all the system and found this system has different subpopulations of globular clusters. We have the typical blue and red, but also we have a very young and very bright subpopulation here. And we know this galaxy the globular system is dominated by the intermediate color subpopulation. Using this data, the photometric data, we estimate the age of the intermediate color subpopulation around 5 gigayears. Then, in the second approach, we get multi-object spectroscopy of the central region of the mosaic in the photometry. So we get a spectra of all the objects you see in that image. They are around 40 objects in total, with an excellent signal-to-noise ratio. We have some of these objects, we obtain signal noise greater than 50. That it is a lot because this kind of data is really expensive in telescope time. Using this great spectra, we were able to determine the kinematic of the globular cluster system and the ages, metallicities, and alpha element abundances of each object. To do that, we use the leak indices, and we compare the leak indices are some features inside the spectra, and we compare them with simple stellar population models. In that way, we obtain the kinematics, and then realized that the sample was dominated for this distinguished subpopulation of globular cluster. I say later that was the intermediate color, and they have ages between 2 and 3 gigayears. That also is the sample of globular cluster, the young globular cluster, most the bigger one in all the galaxies we have. But using this information, you use this information to describe the merger of the galaxy. Using this data, we date the age of the major measure that suffered this galaxy around 2 gigayears ago. And then we were started to use all the different options we have to try to shed light about the minor merger events that this galaxy suffer. How to do that? Well, we are now searching in our data some object that appears to be UCDs, because we know this object could be or massive globular clusters or striped nuclei.
with lower angular momentum in the center. So this can show us that this efficient gas inflow is related to the redistribution of the gas with lower angular momentum. So the gas with lower angular momentum starts to inflow to the center, and this gas maintains the star formation at the center of the galaxy, and the galaxy eventually become compact. So this is the scenario for the dark matter-rich galaxies, and now I will show to you the scenario for the dark matter-poor galaxies. So since all the dark matter-poor galaxies are satellites, I compare the evolution for dark matter-rich satellites and dark matter-poor satellites. And first, for the sizes, we see that dark matter-poor satellites have a more noise evolution in size. And this can be due by, since the different satellites are in different groups or interact differently with the environment. So this can be a sign of the environment effect. But the main thing here is that the second row here is the mass over the maximum mass that the galaxies have in their life. So, for example, and this is for the tripopulation, for the gas, for the dark matter, and for their stars. So, for example, here the galaxies end up with lower gas, lower than 0.4 this value. So the galaxies lose more than half of the gas content in their life at the end of the simulation. This is true also for dark matter. So this is a sign of room pressure and tidal strip, since the galaxy lost the mass at the end of the simulation. But the important thing here is that for the dark matter-rich population, we see that for the stars, they reach that means they reach the maximum stellar mass at the end of the simulation. So at the same time that these galaxies become compact, they continue to form stars until the end of the simulation. But for the dark matter-poor satellites, we see that they end up with lower than half of the maximum stellar mass that they have. So these galaxies, they become compact, losing their stars with time. And this can suggest us that these galaxies become compact by tidal stripping. And we verify that looking to the profiles. So again, here is the profile for the radial velocity of the gas, and below have the profile for the stellar density. And for the radial velocity of the gas, we see that the dark matter-poor galaxies, they don't have the gas inflow since they lose their gas by room pressure. But the important thing here is for the stellar density. So the dark matter-poor galaxies are the dashed lines. So we see that for redshift above 1, the dark matter-poor galaxies, they have more stars than the dark matter-rich galaxies. But with time, they start to lose these stars until the end of the simulation, where we have this cut in the profile. And this is a tidal stripping, a tidal feature of the interaction. So I put here, now here. This cut in the dense profile is a sign of tidal stripping. So these compact galaxies, they become compact by tidal interactions. To conclude, we identify in the lustrous simulation 2 main mechanisms to form a dwarf compact galaxy. The first one is the concentrated star formation, and the second one is the tidal stripping. And we can identify these scenarios analyzing the dark matter fraction of the dwarf galaxy. If the dwarf galaxies have are dark matter rich, they probably become compact by a concentrated star formation. If the galaxies are dark matter poor, they become compact by tidal stripping. So it is, and thank you.
Questions?
Thank you very much for the talk. So I was wondering about if what you are actually seeing is the result of the spatial resolution of the illustrious CNG, because as far as I recall, you cannot resolve anything below 1 kiloparsec. So I don't know if you can comment on
the resolution of the illustrious, at the end of the simulation is something here. Sorry. that I presented here is something here. The resolution of the is very similar to the size of the compact galaxy. But the main thing is that the compact galaxy start to become compact here, redshift 0.5, where the resolution is very low here. So the compact mechanism starts above the resolution of the lattice, and the galaxy become compact towards the limits of the resolution. But the main conclusion is that the resolution is not a thing for the mechanism to become compact, but can become a thing now at the end of the simulation, because it is really in the limit of the resolution.
Any other questions?
So what drives the gas then into the center?
So I will show some slides that I don't show in the main talk, but here I comment about this redistribution of the gas with lower angular momentum. So what we identify is that this is a plot of the evolution of the gas, the recent accreted gas angular is the evolution of the angular momentum of the recent accreted gas. So we compute we take the particles of the recent accreted particles of the gas, and we compute the angular momentum of these particles. And what we identify here is that the compacts, they have they accrete gas with lower angular momentum than the normals. It's a slow difference, but is a difference. For example, here, especially for the centrals, we see that is a difference above the 3 sigmas of inserted. So what we see is that these compacts, they accrete more gas with lower angular momentum, and this gas with lower angular momentum inflow to the center.
But why?
And now I show another plot. Here is the environment of these galaxies. So what we see here is that the compacts, they live in, for example, for the centrals, they live in halos with lower number of satellites, and also they live in halos with small masses. So compacts live in lower density environments than the normals. And this is related to this mechanism to the gas inflow. And also we identified this for the satellites. The satellites are galaxies that fall in the group after the normals. So this is all this is related.
Okay, let's thanks our speaker and move to the last talk from the cluster initial function of AIM82 disk superstar cluster by Bolivia Cuevas Otahola.
Well, hi, do you hear me? Oh, just a technical problem. Okay. Well, so I am Bolivia, I'm from Venezuela, and I'm currently a postdoc in Mexico at Benemérita Universidad Autónoma de Puebla, and working with collaborators at INAOE and IRIA, UNAM. So I'm going to present you some of the results from our recently published paper. Okay, so just to give a brief context, we should recall that star clusters are associations of gravitationally bound stars with masses, come on, sorry. Okay, with masses typically, where's the light here? Okay, here, okay. With masses typically from 100 to millions of stars, and sizes that could be also bigger, but in general, less than 10 parsecs. And we can classify star clusters in terms of their ages, or in terms of their structural parameters. So I know this is very, may cause some debate on the edges, but in the case of this type of clusters in general, we can refer to young clusters as those clusters having ages less than 12 million years, intermediate-age clusters with ages less than 1 gigayear, and finally, all clusters, which are clusters with ages above 1 gigayear. So we have here some examples. And on the other hand, regarding their structural parameters, we can talk about open clusters, which are very distended clusters with low masses, low densities, and that are very large, as you may see, as in Hyades, Pleiades. On the other hand, we have the classical and very well-known globular clusters, which are very old clusters, among the oldest objects in the universe, that have very large masses and densities. And these are very compact objects with, in average, sizes of 3 parsecs. That could be also bigger. And finally, in the last decades, a new classification has emerged, which are the superstar clusters, which have masses and densities resembling those of globular clusters. And for this reason, they are thought to be the progenitors of the globular clusters. As in this case, I show you the very popular R136, which is a cluster in the Triduranos region in the Large Magellanic Cloud. So, but to test or to try to track this relation between the superstar clusters and the globular clusters, we require several tools. And for instance, we have this one, which is the cluster initial mass function. What is this cluster initial mass function? Well, this function can tell us how the cluster masses were distributed at birth, and we can characterize it in terms of samples of superstar clusters, or in this particular case, only young clusters with ages around 12 million years. This type of study has been carried out for several galaxies, for instance, in LMC. Did you see the red point? No, I guess you don't. Okay. So in LMC, in the SMC, antenna, and M51. So in general, it has been seen a trend of this cluster initial mass function following a power law with index of -2. However, for several galaxies, it has been seen that there is a break in the cluster initial mass function, as you may see here. And this is very interesting because you may ask, is this trend universal? So here you might see that it is not. So in this case, if you go for the power law function, you may ask, this power law slope is universal? No. We have found some galaxies that follow a shallower trend, as in this case. This is the cluster mass function, the current cluster mass function of superstar clusters in the disk of M82, which has 1.5. And also you observe here the cluster initial mass function of M82. And this is very interesting since in this particular case, in the work of Mayan collaborators in 2008, they reported that this particular sample they used to build this cluster initial mass function is nearly coeval with sizes close to 10 million years. And in this other case, this other sample is also nearly coeval with ages close to 100 to 300 million years. So this particular galaxy offers a unique opportunity to track the evolution of the cluster initial mass function and to try to understand the processes that may lead superstar clusters to become globular clusters at any point of evolution. So, in the past, several authors have tried to reproduce the current mass function of this type of clusters. In particular, the very popular work by the Greeks et al. 2005, where they tried to reproduce the current mass function of superstar clusters in M82 using initial log normal mass function and initial power law mass function. What did they find? They found that the current mass function is well reproduced by an initial log normal, which is very curious, no? So, on the other hand, in the light of new availability of HST data, in our work, we, in the first place, characterize the cluster mass function for the disk sample. So, we found the current cluster mass function, as you might see, follows a slope of 1.5. And in order to try to reproduce the current mass function, what we did is to explore 5 initial sets of initial distributions, 3 of them which are log normal, as you see here, and 3 of them power law. The traditional one, an expected one with index equal to, and the shallower one, this one. So it is very important to recall that we are fitting this to the sample in IMP08, which is the distribution in Maya et al. Collaborators, which I will refer to as M08 hereinafter. And there is also another sample, which I will refer to as CO21, which comes from my previously recent work, that contains the massive and bright end of the cluster mass function. So you see here, very summarized, these 5 initial distributions. So what's the difference? In the previous work by the Greeks, they used only this analysis in the mass space, to say. But in this case, in our work, we are considering also the values of half-life radius and the positions of the clusters in the galaxy. So to this same and to understand this evolution, we also consider for the first time this also 2 conditions. To say this one, the surface densities of clusters, which has been obtained from previous works, and 3 types of galactocentric radii distributions. One for completeness, for the completeness sake, uniform. This one is the expected one that globular clusters would follow at birth. And this one considering the structure of the M82 disk. So, combining the clustering mass function and these 2, we can populate the disk with simulated clusters in order to reproduce the currently observed cluster mass function after evolution. So, these are, as you may see, only initial conditions. So we need to evolve these initial conditions to the current age of M82. So M82, in this particular case, we assumed an age of 100 million years, which is very close to the spectroscopic ages obtained for the M82 disk. And here you will see the initial conditions I showed you before, assuming several galactocentric radii distributions and also surface densities in these field histograms. And you might see in these ones, in dashed, dotted, and solid lines, the evolution. How did we perform this evolution? We just used each one of these clusters and evolved them separately using a dynamical code called Evolve Cluster of Stars. This is a very simplified version of dynamical code, since if you can imagine, I don't have the computational resources to perform 400 dynamical evolutions with embodied codes. So this is a very good approximation. And once you see this trend of low mass clusters just destroying. So at this point, it is important to recall that this type of distribution does not contain here observational biases, which are crucial, okay, to compare them with the current observations. So, okay, in order to compare these evolved distributions with the observational data, it is necessary to apply these observational biases, which we did using the completeness luminosity function converted to masses using mass to light ratios. So doing this, we finally applied a completeness function, and here you can finally observe The distributions evolved through 100 million years and corrected by observational biases. And you see an excellent agreement in this case, as we expected. You see that in the case of a power law with an index of 1.8, it is perfectly reproduced. And also, you may observe also that in this case, the best match is with galactocentric radii with power law or exponential distributions, not uniform. And also, it corresponds with the less dense initial conditions. In order to quantitatively compare the observed distributions with the simulated ones corrected by observational biases, we used a Kolmogorov-Smirnov test to test whether these distributions came from the same parent distribution. And I report here the p-values for both the mass distributions and also the Aries distribution, which is, as I told you before, crucial. Since previous analysis, they only took into account these disruption times in order to determine how this distribution could evolve. But here we are taking into account that clusters have been reported to follow a mass radius relationship at birth that is lost at some point, since, as we see, GCs, globular clusters, do not follow this. And in order to finally give my almost final remarks, I show you, which is a very, very strong result, the comparison in the mass radius space. So as you see, it beautifully shows an excellent agreement, which is not only in masses, it is also in radii. You see here the average half-life radii distribution here, and here the mass distribution, and this diagram. You can see here in red dots the sample of observed superstar clusters, and in yellow and blue circles, you see the two best fittings, or I mean simulations, that are power law with index 1.8, low densities, low initial densities, and power law or exponential distributions. So my final remarks, we used 5 initial sets of initial mass conditions, cluster initial mass functions, which were combined with cluster initial surface densities. With these cluster initial surface densities, we were able to compute the initial half-life radius distributions. And once we had these masses and radii, what we did was to populate the disk, putting these clusters in several positions along the disk. And we also used a completeness function converted to masses using the mass to light ratio. And most importantly, we established that the observed turnover in the present-day cluster mass function is the result of observational incompleteness rather than to dynamically induced effects or an intrinsically log normal, as was stated before by de Gries. So, thank you.
Thanks. So we ran out of time. So, okay, the call gives me authorization for one quick question from Claudia.
En castellano, a ver. Una pregunta que me sorprende un poco, porque lo que yo entiendo es que los cúmulos globulares son todos muy viejos, sí. Y ahora estás encontrando o proponiendo estos supercúmulos que podrían ser los progenitores de los cúmulos globulares. Me pregunto por qué entonces, si estos son los progenitores, los vemos ahora, entonces ¿por qué no vemos cúmulos globulares de distintas edades, si es que todavía están los progenitores y ¿se entiende la pregunta, no?
Claro, sí, la entiendo perfecto. Esa es una pregunta bastante, tiene muchas vertientes y digamos un poco complicada, ¿no? Porque, por ejemplo, en el caso de galaxias como M82, tenemos un rango de edades muy limitado, ¿no? Entonces, lo que estamos viendo son simplemente cómo se vería un protocúmulo estelar a 100 millones de años. Entonces, para poder ver cúmulos protoglobulares, digamos. En otras fases de la evolución necesitaríamos muestras que tengan más o menos esas, digamos, como que esas edades, ¿no? Entonces, en el grupo de M81, que es donde está M82, hay otra galaxia que es NGC 3077, si mal no recuerdo, que casualmente hace un mes encontramos estos candidatos con edades de 7 y 8 gigaños, y uno como que por 5 gigaños. Entonces, esto habla de que quizás no son muy comunes, y ahí está el debate de saber si son o no, porque necesitaríamos muchísimos cúmulos para poder ver que en efecto estos sean protocúmulos globulares. Por otra parte, en un estudio previo que hicimos en el grupo, teníamos una muestra, precisamente la muestra de M82, hicimos un análisis haciendo simulaciones dinámicas y notamos que de todos los casi 400 cúmulos supercúmulos estelares, que son todos supercúmulos estelares, solo 4 puede ser que lleguen a ser globulares. Entonces eso da una idea de que la mayoría se van a destruir, por eso no se están observando casi. No sé si eso respondió la pregunta. ¿Sí?
Okay, thanks Bolivia again.
Thank you.
We are back at